Um, Today's class is continuing the series of the introductory guidance for the quantum mechanics. So our topic today is what is exactly meaning of the wave function. Either it is in the symbols of two variables like x and t, which is the position and time, space or time, and the other one which is wave function, but it's a function of only the position or space. And what is the meaning of the probability density, which is the absolute of the square root of the absolute of the wave function. So to answer this question, let's start from one of our previous discussed classes about the time-independent and time-dependent Schrödinger equation. And in one of our previous classes, we have shown how to reach the time independent from the general form, which is time dependent. So this is the time dependent Schrödinger equation, the general form, and this is the time independent Schrödinger equation that we have reached. But now our topic is to talk more about the wave function and its meaning and what is the probability density. So let's start from this equation. This is here same. Just briefly to tell us how we have reached the time independent. Previously we have mentioned that this equation of wave function, this is the wave function, and any function which is depend on several variables, we can mathematically write this function into separated different functions. Each function will contain only one variable. So this is psi of x and t. It could be written as g of x multiplied by f of x, or psi of x multiplied by g of x, or any kind of division or divide of functions. And this is the last form. So this is the previous form that it's here, the same one. We have rewrote. This is mathematically definition, and we have substitute into this equation. So this is how it will reach after we are substituting the mathematical wave function after we divide it into a lowercase wave function psi and g of t. So those two functions is the same with this one wave function, but with two variables. And then we have divided lowercase of psi of x g of t for both sides of this equation, and we have got this final form equation. And because we have decided that the left hand side and right hand side, each of these sides has to be constant, and we have referred this constant into arbitrary symbols to be e. This is mean constant, and it could be any symbol as we have discussed before. So our real class would start from this point, this part. We have to rearrange the configuration of this equation, and simply that we can multiply right hand side and left hand side by dt divided by h prime multiplied by I, like this value. So we have multiplied, this is right hand side and this is left hand side. So we have rearranged the equation, and we have got this form of rearrangement equation. Actually, we are interested about this part, so let's integrate this part of the equation. And after integration, because this is a derivative of g of t divided by gt, this is simply its integration would be equal to the logarithm of g of t, and this equation will equal to integration, because all of these are constant. This is constant, this is constant, and this is constant. So this is integration of d of t, it's simply t. But why we have here minus and previously we have plus? It's because we are redefine the complex or imaginary number I. Instead of 1 over I, we have made it to be in the in this side. So I multiplied by I equal -1. So I equal -1 divided by I. So we are substituting this value into this equation, and finally we have got this form. So now, to clear this equation from the len or logarithm values, let's take the exponential. So we are taking the exponential of this resulted equation, and we have got g of t, this is function equal to the exponential of minus I e of t divided by h prime, and this is a blank constant divided by 2 pi. This is also a constant value. So as we have defined previously we have defined that those two functions are generated from one function, because we are mathematically redefined the one function two variable dependent function into two separated function. Each function depends only on one variable, and this is lowercase psi, and this is g of t. So again, if we are substituting g of t that we have got into this value, so psi x of t, again this is psi x of t, this is wave function, would equal psi of x g of t, and it will equal psi of x multiplied by g of t that we have got in this equation. So actually this is the wave function, but up to this point we cannot tell exactly what is the physical meaning, or what is the exact meaning of wave function, because in this right hand side equation there is kind of imaginary number I, and I we have mentioned previously that it tells the complexity, how it's complex. It's like kind of sample how is the level of complexity of the wave function, because it deals with the dual nature of the particle, such as electron in quantum mechanics. So to again clear the needs of using imaginary number I in the wave function equation, let's just simply take the absolute of this equation and then take the square of this equation. So we are taking the absolute of this equation to make it like, why we are doing such thing, we are trying to get some meaningful physical meaning from the wave function itself. Like up to this point, wave function doesn't give any physical meaning, but if we are taking the absolute and square it, we can get some meaningful equation. So in all of these sides, we are defining the absolute and taking the square. So this also has to be divided in the same manner. We are taking the absolute for each function and taking the square, absolute for each function and taking the square. This is simply the square root, the absolute of this value, and taking its square. This will be resulted with 1. So we're gonna remove this values from this final form equation, because this simply equal to 1, and this is approved in several places. You can check, or if you don't understand, I can tell you briefly about how this one reached to be this exponential value reached to be 1. So this is the final form, that wave function, the absolute value, the square root, I mean not the square of the absolute value of wave function, which is dependent of two variables like the position and time. It will only equal in the same time the absolute square value of the absolute of wave function. So the meaning is that the probability, this is meaning the probability of finding electron along x-axis as space, it is also known as probability density. So this is the probability density of that particle, which should be electron, and this probability doesn't depend on time. Like how the probability doesn't depend on time? Like suppose that you have a coin and it has head and tail, And if you are saying the probability of finding it at time 1 equal 50%, at time 2 it will equal 50%. So at any time, like even now or later or in the future, always the probability of finding it always keep to equal 50%. So it's kind of physical meaning, mathematical meaning, fact meaning. So to project such fact onto the wave function, which is probability of finding the electron in the space, it has always to be same. It doesn't change with time. So to this one has to be approved mathematically and physically, and this is what we have approving here, that the probability density of finding electron, it doesn't depend on time. It's not function of time. It's only function of the position. And this is in the beginning of our title of this today's class. We have noted that we are going to talk about what is the wave function, which is function of two variables and only one variable, and it's clearly defined here from the probability density of the wave function, which is telling that if it's function of two variables, it's the same. It's function of only one variable, which is the position, because it's not function of time, since the probability meaning fact physically and mathematically always same. It doesn't change. So this is what we have mentioned today, is what is exactly the meaning of probability density and wave function, its relation with wave function, which has been derivated from the Schrödinger equation itself by rearranging some equation and taking some integration and making exponential into some values, replacing the imaginary number into some other form, and then take the absolute value and square it. Then we have finally reached that the probability density function, it's only function of the position.